Hello everyone, this is Ankur Kumar, Simulation Specialist at Tata Technologies. Welcome to next session of WIGNETs. In this particular session, I'm going to demonstrate how we perform a simple part level structural simulation within the CATIA environment. So CATIA does offer a suite of simulation products that enables primarily designers and design engineers to perform preliminary basic FES simulations both at part as well as assembly level. These are primarily designer centric tools, which means that they don't involve a lot of complexity with respect to the usage, and this is something which can be occasionally utilized by designers to quickly evaluate their design against the design requirements. So a bit about the license, go to tools, options, licensing. So for this particular session, we are primarily talking about this license, GPS, Generative Part Structural Analysis, which can rest over an MD2 or an HD2. Um, and that's pretty much the basic license which is required to perform these simulations. Once this license is procured and enrolled, uh, user can go to the start menu, analysis and simulations, and this GPS would get activated. So before we actually go to this workbench, the one thing that I would like to do is assign some material to this hanger on which we are going to perform this simulation. Let's pick up an aluminum, apply material, okay. It's pretty much here. If I double click on this, there's a lot of information for this material, but from simulation perspective, we are only interested in this analysis tab. So basic linear stress level analysis, all we need is Young's modulus and Poisson's ratio, which is defined by default in the material library. Uh, for some other types of simulations, we may require these quantities as well, like density for dynamics and thermal expansions for thermal simulations, etc. Okay, so we are done with material definition. Now let's go back to our analysis workbench. Now the first thing that application asks us is to provide what sort of simulation we want to do. Default is static analysis, which is the one we choose in case we want to do a stress simulation. So let's say OK over here. Um, now I'll choose the shading type to shading with material. That makes more sense. Um, so we see a green icon over here. If we double click on this guy, this is primarily the octretetrahedron mesh. So we have to discretize this structure into a network of nodes and elements, and we know that designers usually are not familiar with this concept. So the application doesn't ask for lots of advanced input. The very basic requirements that needs to be entered is what should be the size of the mesh and what should be the absolute sag. Size primarily defines how finely or how coarsely this entire structure is discretized, and sag primarily defines that how well any curvatures or complexities in the structure are captured. So application automatically selects some default numbers based on the size of the structure, but user always has a choice to change it, make it more coarse or more fine. I'm making a bit more finer in this case. And then choose the element type. Linear means more faster simulation time but somewhat less accuracy. Parabolic means computationally more expensive but more accurate as well. I go with the parabolic option over here. So that's about discretization. Nothing is done right now. All this discretization would take place when we eventually perform the simulation. Now we see a lots of stuff over here at the top. See, these are different toolbars used to carry out different activities. Here, let's say here we have a restraint toolbar, and I'm going to use the clamp option to primarily fix the structure somewhere. So these two holes are fixed. I select two faces and say OK. And then I also want to put a slider constraint on this face, because this face primarily is connected to some other structure in reality, so I really don't want any perpendicular motion over here. So for such kind of situation, I have a surface slider option which I can use. Select the face and say OK. So that's the restraints definition. Now I need to put a load somewhere as well. So I'll go with a distributed force load. There are a bunch of others as well. The simplest one is distributed force, and I take this surface as the support, and maybe I want to put an 3000 Newton in the z direction. Okay, so that's all I need to do. Basic definition is complete and everything is stored in the tree. So if I go on expanding this tree, everything is there which can be modified or changed. The mesh definition, the material definition, two restraints, clamp and surface slider, as well as a distributed force. Everything can be modified later on just by double clicking and either changing the numbers or changing the location or both. We are all set to perform the simulation, but where does the data go in itself? Let's look at that. So there's an external storage option. If I click on this, it gives me two options: CAT analysis results and CAT analysis computation. These are the two basic output files that are created once the simulation is complete. And eventually we may require these files later if we want to perform some modifications in an already existing solution. So we can either change the location, keep it in some safe directory, or we can keep it in temp as well. Now if I want to compute the simulation, there is a compute icon over here. Click on this one, and then there are multiple options: mesh only, case solution, etc. I go with the all, which means I am telling the application to discretize the structure, apply the loads, apply the constraints, solve it, and directly give me the results. So if I click on save, okay. Now a lot of back-end activities would be carried out. At first there would be some resource computation, how much memory is required, how much hard disk space is required. If we are okay with it, we can click yes and move further, and simulation proceeds, and probably it's complete now. This is a relatively simple and a very small model, so I think we are in a position to visualize the stresses. The first thing we may like to have a look at is deformation, and if I change the option to shading with edges, here I can see how the mesh which we defined in the beginning. So this is the mesh size with edge length of 10 units as we defined earlier. We may like to hide a couple of things which you don't want to see, or maybe this one, hide and show. Okay, so this is how the mesh looks like. I have to go to the shading with edges option to visualize it. I can go back to shading with material. The other output quantity that we quite often ask for is von Mises stress. So these are the stress values, and there's a legend over here that shows the value associated with the color. 1.27 E6 is the minimum and 2.56 E8 is the highest at these two hotspots. There is something called as image extrema, which I can use to actually create a balloon and display the absolute location and value of the displayed quantity. So if I say OK over here, it shows me that von Mises stress is right at this spot, maximum value, and that maximum value is displayed here as well. Can go again to image extrema and deactivate it. The other output quantity that I can have a look at is displacement, and as I go on creating these images, they are stored in the static case solution. So right now the displacement one is activated. I say average ISO and I can have a look at similar plot of displacement, and I can really move back and forth and go on activating and deactivating one of these. It's also possible to have animation in which this structure gradually deforms and the displayed contour, whether it is stress or displacement, is gradually established. Um, that's one option. If we want to have a look at both of these quantities in the same plot, we have to activate both, and there is some option called as image layout. Uh, Maybe let's say 200. Okay. So this way it's possible to display both more than one output quantity at the same time, and we can take a snapshot of this and do a number of things with it. So I deactivate again one of those. Let's keep one at a time. And there's also an option to generate a report, which means um, an HTML file which would have all the information about the inputs and all the images that we generated so far. So if I click on generate report, add created images and give it some title, let's say anger, and let's say okay. Okay, so this is the report. It mentions number of nodes, elements, element type selected, the criteria, the material definition with all the values, the images for boundary condition, constraint, singularity computations, and a couple of images. So this is the deformed image, and this is the stress image, and so on. So that's pretty much about this particular session. In future, I'll be demonstrating some advanced things with the same tool, that is how we perform the assembly level simulations and how we gradually incorporate things like material and the non-linear boundary conditions for such types of simulations. Thank you very much.